squared, and that gives us a induced voltage of 0.19 times 0.09. I get 0.0171 volts, or if you like, 17.1 millivolts. That's for part A. For part B, we know that, the current is equal to the voltage divided by the resistance by Ohm's law. So that's going to be 0.0171 volts divided by the given resistance in the problem, which was 0.6 ohms. And so the induced current by this changing magnetic field is apparently 0.0285 amps, or as I would prefer to write, 28.5 milliamps. I don't know, I like writing things in terms of milliamps. It just feels real. Sorry, I'm an idiot. Let's see here. So that was 29 point what?
That's right.
It's right? Woohoo! All right. So is there one in there that you'd like to work? No, nothing specific jumps out at you. Let me see here. So I would point out that 29.7, I'm just going to make a comment about 29.7. Number 29.7 is good to work. Why? Why would that be good to work? Oh, wait a minute. Funky. Yowzers. Actually, this one here, I would say, I thought it's a class example, but it's a modification of the class example. See, in class, I worked one, remember I worked the problem where we have a steady current and we pull the loop away? This is leaving the loop in place and changing the current. So, I mean, I suppose we can work this one. Maybe. I'm going to work 29.9 instead, though, because I think that one's going to eat up a lot of time and more time than I want to spend on it. But that's a good problem to work. Number 29.9. I think that 29.7 can be handled by the mathematics I shared in class. It's just that I don't know. I'd have to work through it to be sure, but okay. So this one here this is the shrinking loop problem. You have a circular loop of flexible iron wire, has an initial circumference of 165 centimeters. Right, so you've got initial circumference, right, 165 centimeters, and then it's shrinking, right? It's shrinking, and it's decreasing. At what rate? At 12 centimeters per second, all right? Due to a tangential pull on the wire. The loop is in a constant uniform magnetic field oriented perpendicular to the plane of the loop with a magnitude of 0.5 teslas. Find the EMF induced in the loop when 9 seconds have passed, and find the direction of the current in the loop viewed as looking along the direction of the magnetic field. Excuse me. I don't understand the last sentence. So maybe we won't do that, but I will describe the direction in my own words for you here, okay? So why does it, the reason that they want to pull on it, so this is a kind of contrived example, but I kind of like it. You notice what the deal is they're trying to say that as it's being pulled down, it's always a loop, all right? Like it's continuing to be a loop, which means that we can calculate the, let's see here, so what's the area? So the magnetic field is like, like this, let's say. Everywhere. So if that's the case, it's probably a good idea, excuse me, to describe this problem. Well, fine, I guess we can naturally do it in terms of this is kind of weird, but what's the area for a circle in terms of its circumference? Area is equal to pi r squared, right? But the circumference is 2 pi r, right? So that means that r is c over 2 pi. So if we write the area as a function of circumference, we get pi times c divided by 2 pi squared, right? Which is just a weird thing to do, but it's the natural thing to do here. So we get, 1 over 4 pi squared, right? Times c squared. And okay, so the flux then is a times b naught, which is 1 over 4 pi squared. The circumference squared times times b naught, right? So then, what is the voltage induced? We need to differentiate this, right? To find, Faraday's law says d phi b dt. So our, I'm going to just put a magnitude here. The magnitude of the voltage is d phi b dt. I don't care for that minus here. Okay. If you like, I could put a minus here, and there's a minus for the, what is 12 centimeters per second? You understand that that is dc dt? Because that's the rate at which the circumference is changing. We're told that the circumference is changing. So, all right, so d phi b dt is actually, golly, 2c b naught over 4 pi squared times dc dt. Did you see what I did there? I'm doing the chain rule because c is a function of time. This is a lot like the calculus 1 related rates problem, right? Now, all right, so what do we got? So we're looking at it t equals to 9 seconds, right? It tells us that the circumference is decreasing at a constant rate, right? So what is the circumference at this time? So we got 165 centimeters minus 9.0 seconds times, 12 centimeters per second. That should give me, the circumference at the time t. Whatever that is, I hope it's not negative. That would be bad. Like, oh no, it's an unphysical problem. Do you get 56.4? Did you get that? 57? Oh, I made it 9.05. I'm a dummy. So it's 57 actually. Yeah. Thank you. 57. Great. And so here we go. We've got to do, let me cancel the 2 and the 4 and just trade that for a divided by 2 pi squared. That would be more sort of good. So we've got 57.0 centimeters. Oh, phooey. I got to convert that to meters. 0.57 meters times my magnetic field. What was that? I didn't write it down. It was given in the problem. Oh. 0.5 Teslas, right? Divided by my 2 pi squared. And my dc dt. I'm just using everything positive here. Technically it's negative, but I think that's 0.012 meters per second. All right. 0.57 times 0.5 times 0.12 divide by 2 divide by pi squared. I get a voltage of 1.733 millivolts. Yeah. Oh man. Did you get the same?
I did.
9 seconds have passed. Initial circumference. Circumference decreasing. Well. Oh, that's a pi, not a pi squared. See that? Pi, not pi squared. Try that again.
Yeah.
5.44 millivolts. And that is the answer in the back, I think. Yeah. Okay, so how about the direction? I'm not going to try to answer it according to the book's rules. Like I always, when I ask questions about direction on test, I intentionally don't use that kind of language because I don't think it's helpful. Okay, so like, you know, I always try to use language like clockwise or counterclockwise, where it's understood that we're talking about out of the page as being the positive direction, right? So, so for this one, is the current induced clockwise or counterclockwise? So the magnetic field through the loop, right? It's currently what? To start with, it's into the board, right? As you shrink the loop, the magnetic flux going into the board is decreasing through the loop. All right, so the current wants to be induced in such a way to increase the magnetic flux into the board, magnetic field into the board, to get the flux back to where it was. So to increase the flux into the board, you go like this. So the induced current is like this. All right, let's see here. Bum, 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 bum. I see so many even problems I like. It's really annoying. Let's work number 18. I don't care if it's even or not. We're going to work it. All right. I would say I recommend number 15. I'm going to recommend number 15. Good problem. Let us look at, I guess we could do number 22. Let's do number 18 first. I don't think it'll take long. This one here, we've got the current, all right, that this current I is, we're given, it's a function of time, and it's actually I naught e to the minus bt, all right, where b is a positive constant, all right? And then we've got a coil down here, all right? And we're supposed to find the direction, clockwise or counterclockwise, of the induced current in the round coil for t greater than 0. So which way does induced current flow? All right? Now, we don't have to do the full calculus here to answer the question, right? We just need to come to an intuitive understanding of what's going on. So first of all, as you go in the direction, so we're going to assume I naught is positive. That was probably said in the problem. So if it wasn't, it should have been. Physicist, what can I tell you? So it matters because it would flip the answer. So anyway, so if I naught's positive, this is my room. I reserved it. So the current goes this way. And as you think about the magnetic field coming out here, right? It's coming out of the page, right? Okay, so that's at a given time. As time increases, what happens to this? If we graph, current versus time, our maximum is at time 0, and then it exponentially decays, right? So the current's decreasing, right? So that means that, so we got flux. So your magnetic field's coming out at you, right? Coming out at you. So you've got flux coming out at you to start with, right? And as this current drops off, that magnetic field decreases. So that means that the change in flux is into the board, right? You're decreasing the amount of the ones pointing out at you, right? So if you're decreasing the ones going out of you, you want to increase the magnetic field lines coming out at you, which means that the induced current should be like this. Which would be counterclockwise, right? So the answer here should be counterclockwise. Does that make sense? Uh-oh. So we always induce a current in a direction to try to maintain the flux, to try to oppose the change in flux. So let us look at number 15 then. That should help. Okay. So, oh, I thought maybe I'm thinking of the right problem. Oh yeah, we're here. So here you've got a circular loop of wire in a region with a spatially uniform magnetic field, all right? And so you've got magnetic field like this, all right? That means that the magnetic field's going into the page, right? And you've got the loop like so, all right? And we have A, B increasing, B, B decreasing, and C, B is constant. So if the magnetic field is increasing, right, that means that the number, like this, so what this means is that the field lines into board are increasing. So what that means is you want the induced current to make B field not into the board but out of the board. So okay, if we want the magnetic field to go out of the board, right hand rule, so it should be like that way. So we want induced current like this, also known as counterclockwise induced current. Now if the magnetic field is decreasing, that means that the field lines going into the board are lessening. So you want the induced current to increase those to build it back up to where it was, So in that case, you've got clockwise in case B. In case C, this is easier. The induced current 0. If the magnetic field's not changing, the induced current is 0. This is the easiest case of all right? So yeah, that's 15. Counterclockwise, clockwise, no induced current, yeah. So let's see here. Where was I? I think problem, where was it? Oh, 22, is that the one I wanted? '22 is not bad, we could do that one. So you've got a circular, I mean this one we should be able to do pretty quickly because I think they're going to boot us, although they shouldn't boot us because we have this room reserved. you know. All right, so you've got a loop, the magnetic field is into the board, and the radius r is given. Interesting. 0.025 meters the resistance is 0.390 ohms. All right, and the magnetic field's, okay, T equals to 0, B equals to 0. All right. And then it begins increasing with B of T equal to 0.38 Teslas per second cubed times T cubed, time cubed. What is the current in the loop magnitude and direction when B equals to 1.33? Okay, so B is equal to 1.33 Teslas. We can solve that, right? 0.38 Teslas per second cubed times T cubed. So let's figure out what time that is. That is time what? 1.33 divided by 0.38. Cube root that thing. That's the time we're interested in. So it doesn't tell us what time, it makes us figure it out.
Is it 1.33 or wait?
Yeah, for me it's 1.33.
Oh,
So I get 1.518 seconds, all right? So what's the voltage? So to find the voltage, we need to use Faraday's law, right? And Faraday's law is d phi b dt with a minus is the voltage, which in this case is, you know, minus pi r squared times dB dt, which is minus pi r squared times, that is going to be 0.38 Teslas per second cubed times what? Times 2 t squared, right? Differentiate. Oh, I'm in a minute. Derivative of t cubed is 2t squared. That's great. Yeah, how about 3t squared? That might be better. Dummy. Me, not you. So that's the voltage. The current, which is what we're asked for, is the voltage divided by the resistance, right? So we got to do minus pi times the r squared times 0.38 Teslas per second cubed times 3 times the time we found, 1.518 seconds. And that's all divided by the resistance, which was given, 390 ohms. And that would be how you do this problem. Right? So we can work that out, I suppose. 0.025 squared times pi times 0.38 times 3 times 1.518 squared divide by 0.39. I get a current of about 0. I guess it's a negative technically, minus 0.0132 amps. Or if you like, minus 13.2 milliamps. And that being negative, right, that would mean that instead of going into the board, it should be that the current is induced in this direction, I think. Yeah, it should be induced in, so like the induced current would be this way, which is what, counterclockwise? Yeah. That makes sense because the magnetic field is building up. See the way that makes sense? The magnetic field here is building up into the board. So the magnetic field lines are going more and more and more and more into the board with this formula because it's getting bigger and bigger. So the induced current has to go the opposite way to try to, keep the magnetic field coming out of the board to be more. All right. It doesn't succeed, but it tries to stop it. I mean, ultimately the flux does increase into the board by that formula. But anyway, so there it is. So I guess we have one. I guess next week we've got another one of these, right? And I think that's it before the test. So maybe next week we'll focus more on like circuits